So you're going to want your formula sheet out, and you're going to want your right hand ready. We're going to be doing a lot of combinations of stuff. So hopefully by now I've convinced you that a charge that moves through a magnetic field feels a force. It gets deflected. I showed you a video of a wire jumping. Did I show you the TV screen with the magnet making the TV screen look like it was melting? I'll show you that one later on today. You were the group I forgot to show that one to as well. How can we calculate the magnitude? Well, it turns out we're going to start out looking at a single charge, and then we're going to extend that to a wire, which is basically trillions of charges all holding hands. So on a single charge, the force, and I'm going to use F with a subscripted B for magnetic force. B is our symbol for magnetic field. Depends on three things. How big the charge is, Q. Bigger charge, more force. Smaller charge, less force. How fast the charge is moving. Make sure you see that's a lowercase v. I did not put the wings on it. It's not a voltage, because we are seeing current and other things showing up here in a little bit. And the strength of the magnetic field, B. But there's a restriction. Look up. The velocity and the magnetic field have to be perpendicular to each other to get maximum force. It's if you think about the right-hand rule thing, they're all at right angles to each other. Thumb points up, finger straight ahead, palm that way. If they're not moving perpendicularly, you would use a component, and if you draw it out, you'll find actually the component of the magnetic field that you want is sine theta. And so a better equation, don't write this down, it's there, is F equals QVB sine theta. I just want to convince you that it works. If theta is 90 degrees, what's the sine of 90 degrees? 1, and you get QVB, like I put it in the box. If theta is 0 degrees, so that it's running parallel to the magnetic field, what's the sine of 0 degrees? And you get no force. That explains that electron question that I ended last day's lesson with, where we said that electron would go in a linear direction because it wasn't cutting across the magnetic field. I am not going to give you any component questions in this unit because I've had to rush too much. So the maximum force is experienced when particles move in a direction that's perpendicular to the magnetic field. Cool. Let's crunch it. It says this. A proton moving at 1.6 times 10 to the 6 meters per second enters a 0.15 Tesla magnetic field. Pretty big magnetic field. At right angles to the field. Let's call this first part part A. Let's call this second part part B. Alec, what does A want me to find? Do you say force? It wants us to find magnetic force, and that is just plug and chug QVB. The V and the B have to be at right angles. You don't need to put the perpendicular in your homework. I'm putting it in our notes just to make sure I let you know I did double check they are at right angles to each other. And I'm not going to try and trick you or anything like that. Q. It's a proton. Oh, this is good review.
1.6 times positive 1.6 times.
Well, we're not going to worry about the positive or negative. We want a positive force here anyways. V, 1.7 times 10 to the 6th. B, 0.15. What do you get? Connor.
4.08 times 10 to the negative 14.
Rounded off properly? 4.08. That's round. The 8 is right?
Yeah.
Okay. Times 10 to the negative what?
14.
And that's newtons. It's a force. Is that big? You know what? Let's find the acceleration. Part B. Connor, how would I find acceleration if I know force?
F equals how many?
Yeah. So you're saying I can just go A equals F over M, where F, you know I'm going to use my answer button. I'll write 4.08 times 10 to the negative 14. M, it's a proton. Oh, this is good review. It's on your sheet, right? I remember it begins with a 1. 1.67 times 10. Okay, what's this thing accelerating at? Ah, the sound of people unstrapping their calculators. What a great sound. Sorry? 2.4 times 10 to the 15th? 13th? Isn't that faster than the speed of light? Isn't that impossible? First of all, is that a velocity? No, nothing that says that acceleration can't be bigger than light, because acceleration is in velocity. This proton would not be accelerating at that acceleration for long enough to get to the speed of light. And even if it tried to, who remembers from our relativity unit last year, as your speed increases, what happens to your mass? So the m right there would get bigger and bigger and bigger. What happens to your acceleration then? Nature's taking care of itself. Nice try. No. You're not going to be able to get that proton to the speed of light. Nuh-uh. Okay. That's not the cool part. This is the cool part. Bryce, example 2 says, consider a what? Electron. We don't do electrons. Our right-hand rule doesn't work for electrons. Which way is this electron moving, Bryce? To the? Which is the same as a proton moving to the? So let's all of us use the board behind me as our piece of paper. Let's all of us point our right hands in the direction that this proton is moving, which is to the left. What do those X's mean? What direction is the magnetic field? Down? So I would point my fingers, into the page. I point my fingers into the board. Yes? Justin, which way will this electron feel a force?
Yeah.
So the electron is going to do this. Pause. Now this electron is traveling down and right. Bryce, what's the opposite of an electron going down and right? A proton going? And? So everybody point your thumbs up and left. Fingers still into the page. Now which way will the electron get deflected? Kind of diagonally this way? And then kind of diagonally this way? And then kind of diagonally this way? You can keep following with your right-hand rule. Hey! What shape do you see? This electron will be forced into a? No. This means, are you ready? Are you ready? Are you ready? This means we can say, magnetism is pushing me in a circle. Unlike gravity is pushing me in a circle, here it's magnetic force is pushing me in a circle. This is why particle accelerators are built in the shapes of circles. This is why the Large Hadron Collider is circular, because it's really easy to naturally bend particles in a circle. An electron is moving at 3.2 times 10 to the 7th. It enters a perpendicular magnetic field and traces out a circular path. Kiana, what does example 3 want me to find? I like example 3. I like example 3. I like example 3. Example 3, will you marry me? What's it asking me to find? Magnetism is pushing me in a circle. What was our equation for magnetic force on a particle? We just wrote it in the box on the previous page, or it's on your formula sheet. Q, V, B equals. And then just watch for a second. I'm going to do a thought process. Don't write this down. I would say it's MAC. Stop. Don't write that down. Which version of A do I want to use? It's pretty obvious if you think about it. The one with the V in it. Darn right, because there's already a V in the question. So write this down. QVB equals mv squared over r. This is the particle accelerator equation. Oh, I also notice one thing. What do you notice? One of the V's cancels. And now I got to go on a bit of a rant because I do like this question. But there's I don't use this very often, a dumb error kids make. Kiana, what are they asking me to find? Where is the R right now? I see a lot of kids say, oh, I'll divide by MV. Now I've got the R by itself and I'm done. No, you have 1 over R by itself. Don't make that silly, that dumb mistake. Don't do that. How are we going to get the R by itself? Times it to the top, yes? The MV stays where it is. And Kiana, walk me through the last little bit. Yep. In this equation, how many variables do you see? 5. As far as I'm concerned, I can give you any 4, find the 5th. And this right here was the beginning of particle physics. Usually we knew the radius. We would often run, so if you're ever wondering, like, how did we make the atom bomb in the late 1930s and early 1940s? We didn't have computers, we didn't have fancy equipment. So how were they doing all the subatomic particle physics? We would use something called a cloud chamber. It was a chamber that would fluoresce, that would glow when charged objects traveled through it, and you would have a camera mounted above the chamber, and so you would literally see a charged object go like that, except make that a perfect circle. And from that arc, you could extrapolate the radius. You would know the radius, and then you could either solve for the particle's mass, or its speed, or its charge, depending on what else you knew. It's very low tech, but it worked really well. Cameras, cloud chambers, and this. M, it's an electron. V, 3.2 times 10 to the 7th. And we already know how we can get electrons to move, parallel plates, right? Q, it's an electron. Connor, I want R to be positive, so we're going to do no negatives in this. I think you had earlier said positive. Before, I think it was, yeah. So that's why I said we need to worry about it here. 1.6 times 10 to the negative 19. And the magnetic field, 5.45 times 10 to the negative 4. I hope we get a nice answer. I was doing ballpark figures in my head. I'm hoping I didn't end up with a radius that's so small that the human eye couldn't detect it. I was trying to aim for around half a meter-ish, I hope. 0.3, 0.333? 0.334? Okay, that's not bad. That's about, yeah, we could detect that easily. A couple years ago when I made up a question like this, the radius was like times 10 to the negative 8 or something. It was so small we wouldn't have spotted it. I made up bad numbers. Okay. Example 4. A proton enters a magnetic field at location A, and it traces out part of a circle. We get that with a camera by looking at its glowing path that it leaves behind in a cloud chamber. The radius R is 3.25 meters. The magnetic field strength was that. What's this question want me to find? Magnetism is what's pushing me in a circle. Something's got to be pushing me in a circle. Actually, you know what I should have said? What path is this proton tracing out? And you would have all said, circle. Which way is the acceleration? Toward the center? Good. This is a nice review. Yes? What's our magnetic force on a particle equation? QVB. I did a quick check from the diagram. We are at right angles, so it will curve. I did a quick right-hand rule check. I pointed my thumb up the page, magnetic field into the page, and I just followed the force, and yeah, it would bend it in a nice circle. Emily's now convinced by that one. Yeah. And mv squared over r. One of the v's cancels. By the way, what if I just multiplied the r over? What would I have left behind over here? The m and the v. What is mass times velocity?
Momentum.
What?
Momentum.
So If you don't know the mass or the velocity, but you know the charge and the radius, and you know how big the magnetic field is because you're creating it, you know the momentum. We can use this in particle accelerators when we're smashing particles together. Wham! They collide. We have their momentum, even though we don't have their mass or their velocity. Hugely useful in particle collisions. We can predict collisions without mass times velocity if we know the charge and the magnetic field. Yes? Nice. My last class, nobody saw the momentum. Candy for you later, Connor. But we're trying to find V. So you all agree with me, V is going to be what? QBR over M? Yes? It's a proton, and it's a proton. What do you get? Hopefully less than the speed of light. Wow, lots of typing. Emily, what'd you get? 6.2 times 10 to the 6th. Anybody else? Yep. Put your pencils down. That's for a single charge, Emily. What about for a whole bunch of charges inside a wire holding hands? The jumping wire that we showed you the other day. What would the force be there? We can derive an equation by starting with a single charge. Here's our single charge equation. I know that current is Q over T, so do me a favor, get the Q by itself. If current is Q divided by T, what's Q equal to? Rewrite that to get the Q by itself. Sorry? IT. So where the Q is, I'm going to replace the Q with IT. It's still QVB. And then do me a favor, Devin. Circle those two, the T and the V. Because distance is speed times time. It's really D equals VT plus a half AT squared, but in the wire, they're all moving at a constant speed, so there's no acceleration. So I can replace that V times T, I know it's TV, but that is V times T, with a distance. I can actually replace it with I times D times B. Now, we're going to pause. Here's what I wrote. The magnitude of the force depends on three things. The strength of the magnetic field, did we end up with a B in our equation? The magnitude of the current, did we end up with an I in our equation? And I said it depends on the length of the wire. Did we end up with a distance? And I'm going to use, instead of D, I'm going to use L for length, just so I don't confuse that with my kinematics D. Here's the equation. FB on a wire equals Bill. We usually write it that way because it's a dumb easy way to remember it. Oh, but we have the same restriction as before. The magnetic field and the current and the length of the wire all have to be at right angles to each other. Otherwise, your right-hand rule doesn't work and there is no force. Or it would be a component. So, example 4 says, find the magnetic force and the direction on this wire. Well, let's crunch the magnitude first of all. This is a wire, so it's going to be Bill. What are some dumb ways that I can remember that this is a wire? Current. Oh, you'll also notice I always handwrite my L. I would never write a lowercase l like that, because what does that look like? A 1. In fact, did I handwrite it on your formula sheet as well, I hope? Like, is it a cursive L in your... Yeah, okay. Took me a while to find a font that would let me do that. Magnetic field is 6 Teslas. That's a big magnetic field. That MRI machine video that I showed you was 4 Teslas. Times 5 times 0.7. I can do this in my head. 21 newtons. Double check me, but I'm pretty sure I'm right. Yeah? Direction. Try the right-hand rule on your own for your piece of paper now. So you have to put your pencil down if you're right-handed. You point your right thumb in the direction of the current. Magnetic field is which way? Connor, magnetic field is which way? Look at the arrow where it says 6 Teslas.
Yeah.
So you're going to have to, okay. Magnetic field is down the page, is it not?
Yeah.
So your fingers should be pointing down the page. There you go. Which way is your palm pointing? First of all, don't do this. Flat hand. Lift your thumb off the paper. That's better. Always want our fingers like that, right? So if I was doing it up here, I would go field to the right. The magnetic field is down the page. For me to do that, I have to drop my hand down to my waist, and my palm is pointing into the page. If I was doing this on Connor's piece of paper, just leave it where it is, I would go to the right, like that, and I'm pushing into the page. Yes? It is into the page? So, 21 newtons direction into the page. Oh, although we also have a handy symbol for that. What was our symbol for into the page? If you did that, I'd be cool too. Yeah. Quick look, bunny. Josh, what does example 5 want me to find?
Magnetic field strength.
What variable is magnetic field strength? So look at the equation that we wrote in the previous question. Which of those letters is magnetic field strength? Turn back a page, look at the formula in the box. Or is that on the same page still? On the previous page? Which is magnetic field strength, folks? B. Okay, how would I get the B by itself, Josh? No, okay. So you're telling me... Now think about what you have just said. I can predict ahead of time how big a magnetic field I need to apply a force. We're starting now to get to the physics of, you may have seen at junkyards, those cranes that pick up cars magnetically. This would allow you to predict how much force I need to pick up a car, how strong a magnet I need, or really what you would do is you would adjust the current. Okay, we want a force of 0.001. 1 times 10 to the negative 3. I is 12, and L is 0.05. How big a magnetic field do we need? What'd you get, Brees? 1.67 times 10 to the negative 3. Are we okay with that? Ah. Is that right? What are the units for magnetic field? Teslas. Okay. Brackets? Was it brackets? Really? I saw the frowny face and I thought, I could make my guess. I'll let her figure it out because she'll remember better because she'll be mad at herself. Negative 4 is negative 3, isn't it? Did you do a 0.05 on the bottom and a 0.001 on the top? Or did you do a 0.5 on the bottom? Okay. It's negative 3. Applications. Here's a cool one. There was a movie that came out about 20 years ago based on a book that came out about 30 years ago called The Hunt for Red October. Anybody seen the movie? It's actually a pretty good spy Cold War movie. The book and the movie take place at the height of the Cold War between the Americans and Russians. And the premise is a Russian nuclear submarine captain has decided to defect with his brand new submarine because the submarine is invisible. Not to the eye, but you can't hear it when it's underwater, and all of the United States systems listen for propeller noises. And the reason you can't hear it underwater is they have invented a submarine propulsion device with no moving parts. It's called the Magneto Hydrodynamic Drive. Here's how you can build a jet engine underwater with no moving parts, which would be really quiet and pretty cool. Here is a side view of a mini submarine, except there's one thing that I've removed from the diagram. Don't write this in. Connor, there's a great big metal plate welded right there, and I'm going to charge that up, and I'm going to charge it up positively. Okay, don't write that in. You have to use your imagination. Because seawater is so conductive, those positive charges are going to flow to the metal side of the submarine. The same way that if you dropped an extension cord in water, it would flow through the current would flow through the water to the nearest metal. Okay? So the current, I, is flowing into the page. That's what those X's means. But what's carrying the current is water molecules. So everybody, we're going to use this board as our piece of paper. What direction is the current going? What do those X's mean? So everybody point your right thumb into the page, please. Oh, magnetic field lines point from what to what? So the magnetic field is going this way. So point your fingers in the direction of the magnetic field. I have to hold my hand like this. Like this. Use the board. That's why I said everybody can use the board. So we're all doing the same thing. Which way is your palm pointing, Taylor? Which way will the water molecules feel a force like a jet engine out the back with no moving parts? Ta-da. Oh, and it would suck in more water on the front. It would be very quiet, very difficult to detect, in theory. So they're working on that. Questions that you can start right now. You can try number 1. You can try number 2. Now, in number 2, it's saying that this object is floating in midair. What that really means is that the magnetic force is exactly canceling out gravity. And you know what? Since we're on Earth, we can use little m, little g. That's where you're going to start with. They use Fm for magnetic force. I like to use B to reinforce that B is the variable for magnetic field strength. Right? Right. You can skip 3. You can skip 4. Don't cross out some of these, because solenoids I'm going to talk about next class. But right now you can do number 8. You can do number 10. You can do number 11. 13. 14. 15. And 16. And 17.